Right, so let's define density. So density is defined in terms of two scalar physical quantities. So it captures mass and it captures volume. So both are scalars, and therefore density is a scalar. Now for mass, we typically use the SI units of kilograms, but you certainly can use grams as well if you like. And for volume, we typically use meters cubed, but especially if you're doing densities for liquids and sometimes even for gases, you may be utilizing milliliters or liters as well with regards to that. And you should be comfortable in doing all the different kind of conversions on the units if it's necessary. But in the beginning, you pretty much will find kind of some standard common units for those, and that will be kind of kilograms on the mass side or grams. And then on the volume side, you typically might see just kind of milliliters, liters, possibly cc's, which just means centimeters cubed, and then the standard, which is meter cubed. All right, so those are the ones that you will see. Now, density is defined for all the different states, so it doesn't depend on a particular state. It will have any state that you like. So for example, you certainly can define solids and have densities for various solids. So you can have the density of aluminum, of gold, okay, of your bones, so you can certainly have densities of those kind, and then I will provide you some examples, and we actually do those by experimentation, which is kind of neat. You can certainly move over and have densities for liquids. So here's kind of examples with regards to liquids, and obviously on the liquid side, those densities are going to be actually comparable to solids very often. And don't be surprised, that you will have some liquids that might have actually a bigger density than a solid, which is interesting. Okay, but it's not going to be as common as you think. But there is one in particular, H2O, that has something interesting happening. Now, in any regards, this of course can also have densities which are defined for gases. Now, gases are so sparse, right? The distance between them is so far, so that means they occupy quite a bit of volume, and then there's very few atoms or molecules, I'll just say particles that are kind of flowing around in a volume. So you'll have a huge drop-off, okay, in density, so how much volume those gases are going to take up. So now, what is the actual kind of definition of this? Well, the density is defined in this particular way. Now, we use very often this symbol, which is going to be rho, and it is equal to the amount of mass that you have per unit volume. And that is actually what the density is all about. So it is how much matter do you have, and then how much volume it occupies. And if you recall, from going way back, if you were kind of thinking about how to define mass, and I can put up a link up above there for you to that introductory side, you will recall that mass was actually kind of dependent on both. Does it occupy a certain amount of space, okay, and then can it be weighed in a particular way? Those combinations of those two were useful, and now we are thinking about that in terms of densities. So you can see here that I put the SI unit, and the SI unit is kilograms per meters cubed. Now, a meter cubed, which is basically 1 meter by 1 meter by 1 meter. So if you think about that, 1 meter is actually quite a big of distance. And if you have, cube like that, it's quite a lot. So you are going to be able to pack in quite a lot of matter inside of that. Now, where does these, densities, why do we kind of study them as a physical quantity? Well, because they do have certain properties and various things in terms of that we study. So if it's, aluminums, from golds, bones, water, of course, okay, in liquid form and gas form, oxygens, carbon dioxides, maybe blood, plasma. So any of those, though the characteristic of density is actually kind of useful to know. It tells us, when things are floating and when they're kind of sinking, so that is all dependent on density, and you're going to be running into that. Now, the other item, okay, with regards to this is, of course, this concept of volume, okay, that you have, and I'm sure that you're kind of familiar with volume, so the amount of space that something has, you're going to be needing to be kind of flexible in the sense of being able to convert, right? So different volumes back and forth. Now, there is one density which also gets sometimes introduced, especially once you study weight, and weight is dependent on gravity. And in that case, there is a very special density which is called the weight density, and I'll introduce this here, okay, for the moment. Now, when I write this, very often, okay, what's going to happen is I'm going to write it and it looks like a P, and you might confuse it, okay, with possibly maybe pressure or something like that. So please forgive me, okay, so it is rho, okay, so this is rho. But coming back to this weight density, so what this will be is if you want the weight density, then instead of having mass in the numerator, you would have the weight of an object, okay, or a substance, and then you would divide it by volume. Now, please recall that the weight is nothing else but simply mass multiplied by gravity. So whatever gravity, well, typically we hopefully are going to be on Earth. So this is going to be the definition of the weight density. And this upper one, okay, that you see right here is typically referred to as just simply mass density. But if somebody says density, they typically will be referring to the mass density. All right. Now, with regards to volume, so if you're thinking about, I do want to give you a little bit of a gist on volume. So if you're thinking on volume, one thing that you should be aware of, because not all containers are going to be a nice square, okay, or a nice kind of, cubic shaped in some way, okay, where it's very easy that you can calculate volume. So volume, you can take in and you can say, oh, okay, so this is length times width, times height, and this is going to be for, a three-dimensional, okay, kind of item that you have. Now, it doesn't have to be a cube that you're having, but maybe it's some kind of a prism or something like that, okay, that you have in there. And this is not always the case, and of course, okay, what happens is that we very often have different volumes, and sometimes maybe you'll have a circular base, okay, that you have in there, okay, and that circular base, and then, this kind of goes up and creates a cylinder for us, right? So then we have a cylinder like so. And if you wanted to calculate volume, so one thing that you should know is you should always kind of take whatever the area of the base is. So whatever that base area is, let's call that area just A, let's say this is just A. And then it's just simply multiplied by the height, right, of whatever that is. So whatever shape you have at the bottom, as long as you know what kind of the cross-sectional area is, then you can just multiply it by height, and then you'll know how much space it occupies. So I want you to know that in general, you're going to have, some area, which is going to be the cross-section area multiplied by height. Okay, so that's something that you should know and run into yourself. All right. So now these densities, here I present, to you a few. Now, by the way, you can look up many of these on the internet. So these are not ones that I remember. I do kind of pick them off. So they're not kind of from my own memory or from my own experiments that I have done. But here are just a few examples. You can find many, many more. So for example, in terms of solids, so notice we have aluminum, I put gold, and then I put kind of bone, okay, that we have, and then it gives us the densities, and notice that they're in kilograms per meter cubed. So these particular densities that we have, they just tell us. Now, don't forget that because this is in scientific notation, you can certainly expand this, right? So this is going to be 270, because it's 3, right? This might shock you. So it's 2,700 kilograms, and you'd be like, wow, well that's a lot. Yes, because a meter cubed is quite a big volume. So all of these are going to be relatively big, and that's why we kind of use scientific notation here. But we also, of course, use scientific notation because we want to point out that we have, 3 significant figures here. So this is also 3 significant figures, and this is 3 significant figures, because these are coming from experimentation. And they're not always going to be identical. You might look them up and the answer might be a little bit different. And the reason for that is because when these densities are calculated, they actually do depend on other things. So if you think back of thermal energy, and as you add more thermal energy into a substance, it starts to possibly expand or possibly contract. as you're going through because it just carries in more energy. So depending on what temperature you are at, the densities might possibly change. They may not change by a lot, but they may indeed change. So this is not something that in the beginning you're going to be asked to think about, but your teachers most likely will give you these densities, and then it's somewhere you probably will look around. It's going to be a little bit of an assumption that says, well, this is kind of at this particular temperature, and then maybe this is the actual pressure there as well. So for example, these ones, I actually kind of have taken them off, and we can make the assumption that they're around 0 degrees Celsius, unless it's stated otherwise. So you have all of these, right? And notice that they're all 10 to the 3. Then you have a couple of liquids. Notice the liquids are definitely, less than the solids, but that's not always the case, all right? So don't think that that's always true. So that's not something that you may run into, okay, within here. Now, water, okay, is just 1, okay, and this, notice, it's a perfect 1.000 times 10 to the 3, but this is at 4 degrees Celsius that you have. Notice that, the human plasma for blood is a little bit more dense than water itself. It's 1.03, which is 10 to the 3, okay? But then if you go back in and you look at gases, notice that there is no times 10 to the 3. Well, that kind of should make sense because gases, there's not a lot of gas that you're going to be packing into a meter cubed. Now, it still is, notice that it's still in kilograms, so, you can still have about a kilogram or a little bit more of a gas, but it's quite a big, okay, volume if you're going to be talking about a meter cubed. How would we use these densities, and then how would we do the calculations? It turns out that if you look at this equation, it's not very difficult. In physics, you certainly have run into much harder formulas than this. This is going to be one of the easier ones. And notice again, this is all scalars, right? So there's no vectors involved here at all. So this is just a scalar. So if I go down here, okay, so I've just kind of prepared a few examples for you, and let's take a look at these examples and try to solve them. So it gives you a sense of how would you utilize this density equation to solve this. So here it says we have a sample of blood, okay, plasma, and it has been taken. So the volume of a sample is approximately 8.5 milliliters. Okay, so we have that which is given to us. What mass, and notice we want the mass in grams, would this sample have? Now we can assume, and this is a common assumption, that 1 milliliter will equal to 1 cc, which, by the way, so for this, okay, is just nothing else but centimeters cubed. So the centimeters is the first C, the cubed is the second C, and we just call that cc's. So that means that we have this relationship, okay, in between. Now, if I wanted to solve this, okay, so if I go through, I kind of would have to look up, so this is the blood plasma, right? So we would need the density for this. So the density of blood plasma, if you kind of go up here, so notice here it is, it's 1.03. So I'm going to just write it down, 1.03 times 10 to the 3, but this is in kilograms per meter cubed. And what we want is we want to be dealing with kind of milliliters, okay, in this sense, and then also in grams. So what I wanted to actually point out to you, if you do get given the density and it is in kilograms per meters cubed, you can very easily, okay, change this. Now, you of course can do your unit conversions and you can change kilograms to grams, right? So that's one thing. And then you can certainly change meters cubed to centimeters cubed, okay? And that will be per milliliter that you have. But if you do that conversion, it is nothing else but simply taking and doing this, dividing by 1,000. So that entire process of the unit conversion, if you have kilograms per meter cubed, and you want to be able to change this to grams per centimeters cubed, right? So if you do that, which typically is grams per milliliter, all you actually have to do is divide by 1,000. Now, if you ever forget, then unfortunately you have to go back and do the whole unit conversion. Now, that's going to be something that you can do. But this is a very, good trick, which means that all you're doing is, if you divide by 1,000, that means this whole thing is going to be gone. So this is going to be 1.03 grams per milliliter. So that's what you have. Now, once you have this, because of the fact that density is just mass divided by volume, so notice I can now substitute all of this in here, right? So I can substitute the 8.5. So that would have been the volume, which is 8.5 milliliters. And then I can solve for the mass, which is going to be nothing else but 1.03. Okay, so this is going to be grams per milliliter multiplied by 8.5 milliliters, and you're going to get your mass because the milliliters will cancel. So if I bring this out, 1.03 times 8.5, so we'll have, so this is going to be now equal to 8, and notice we have 3 significant figures here, 2 significant figures here, so I'll leave it to 2. It's going to be the lowest amount, which is 8.8 grams, and that's your mass. So very close, right? A little bit more, okay, than what you have in milliliters. All right, so that's one example, and this is a nice key feature. Okay, if you're going back between kilograms meters cubed and then grams per milliliter or grams per centimeters cubed. Here's another example. Now this one is with a bone, okay, and this particular bone, so what do we have given? So notice 3.8 kilograms. So that's the unit that we have, and it has been diagnosed for possibly maybe some disease. So what volume would this bone occupy? And then provide your answer in centimeters cubed. Okay, well, so within here, well, we have this in kilograms, right? Now this is the mass. So we kind of would have to look up, and again, so this is for the bone, right, what the density is. So if I scroll back up here, now this would be given to you in the question, or you would have a table to look up these densities, right? People wouldn't be necessarily trying to make you memorize these. Now a bone, so that's right here, it's 1.80, right? So this is 1.80 times 10 to the 3, and this would be kilograms per meter cubed. Or, okay, you can say by dividing by 1,000, it will be 1.80 grams per milliliter or per centimeters cubed. All right, so that would have been the same thing. Okay, so you can go back and forth in between there. All right, so now if I have that, because of the fact that I want to be able to know what this is in centimeters cubed, right, and I want to be able to know what the volume is, so now I can go back in this and I'm going to change this. So 3.8 kilograms, that's just a prefix. So that's going to be 3,800 grams for this bone. And now if I go into my formula, so this is going to be mass over volume, substitute everything back in here. So 1.80, this is grams per centimeters cubed. I'm going to drop them because I have those units now everywhere. The mass is 3,800 grams, and then I want to find out what the volume is. So now moving the volume, okay, on the other side, this is going to be 3,800 divided by the density, and there you have it. So now if I do that, 3,800 divided by 1.8, and we have, so this is quite a big volume, and this would have been to 2 significant figures. So this is going to be 2,100, okay, centimeters cubed. Okay, so that's what you would have for this. Okay, so that's how much it would occupy for this particular bone. Now 3.8 kilograms is, it's quite enough. You can certainly do some bicep curls with those, okay, within there. And here's a last example, okay, that you have. So we have a container with an irregular shaped bottom, right? And it has a cross-sectional area of 25 centimeters cubed and is 21 centimeters tall. So this is exactly what I was referring to when you are dealing with volumes. So for example, you can say you have this. You have some irregular shape. Now, whatever shape of that bottom is doesn't matter. And this, has a certain height. Okay, so you're going to assume that that height goes up. So you want to know what this area is. So that area, they're telling us, is 25 centimeters cubed. And they're telling us that this container is 21 centimeters tall. So that's the height. So our volume is nothing else but the area times the height, whatever we have there. Okay, so that would have been for 3 dimensions. So in that case, this is 25 centimeters, sorry, this is squared. Okay, so this right here, because it's area right there, this should be squared. Okay, so let me just erase that. And we would have this right there, because areas are indeed in centimeters squared. Centimeters cubed would have been the actual volume. Okay, so coming back to this, so this is going to be times 21 centimeters. And now you can do that calculation. I'm not going to do any kind of rounding in here at all. I'm going to just leave it for the moment because it's not my final answer. Now it's centimeters cubed because centimeters squared and centimeters, so that's centimeters cubed for the volume. Now let's see what else that they gave us. If the container is filled with an oxygen gas, okay, so we have, oxygen in here, so inside, and let's assume that it is, so this shape would have been the same up top as well, and we're assuming that it's closed in because if it's open, the gas will escape. Then what mass of the oxygen is inside? So provide answer in grams. Okay, so we can certainly do that. Now, I hope that I have oxygen as a gas. Oh, I do. Okay, so it's just 1.33. So notice this is, okay, the density is 1.33, but it is not, right, times 10 to the 3. Okay, it's not that dense. You don't have a lot of matter inside there. So this is kilograms per meter cubed. Now, because of the fact that they want this thing in grams, and we have our volume in centimeters cubed, it's easier for me to just say, okay, let's divide this by 1,000, right? And then change it to grams per centimeters cubed. Now, dividing by 1,000, right? So if what you would have here, so this would turn out to be, you can write it in 2 ways. You can write it in scientific notation, okay, certainly. So this is, divided by times 10 to the 3. Division means it would have been negative, so this would have been 1.33 times 10 to the negative 3 grams per centimeters cubed. Or you can just write it normally, okay, in decimal notation, okay, like this. So that will work as well. So whatever it is that you like, but you should be comfortable with both. Okay, so now that we have this density, now I can just jump in. I also have the volume. So if I go back in for the mass and the volume and start substituting everything back in here. So if we have all of this, the volume itself was 525, and I can now solve for the mass. Okay, so that would have been multiplying both sides by the 525. So 0.00133 times 525 equals, and so here you go. So that's your answer. Okay, so it's going to be not that much, 69825. All right, and this would have been in grams, right? So that's what you would have actually for this. Okay, so this is what you would have, okay, in terms of, so, not even a gram, okay? And looking back for significant kind of figures, so we had 2, I guess, 1, 2, 2, okay, and then the density had 3, so we can certainly put this to 2 significant figures, which is going to be this, okay, rounded. All right, so those are pretty good 3 examples to get you started on density. And density, the formula itself is not super hard, but you're going to run into these examples and you should get comfortable in calculations. If someone gives you the mass and volume, then calculating density is rather simple, right? You can just plug it in, but the ones that I've shown you is you have to solve for either mass or volume as well, and you have to look up the density. All right, okay, so now you're introduced to density. Okay, thank you for watching. We'll see you in a future video. Happy studying. Bye, everybody.